Uh, did almost all this problem in a previous recording. I just want to we'll finish it up here. It was the steady state temperature in a heated cylinder. We assumed radial symmetry so that this was the governing partial differential equation. Boundary conditions are the temperature is held at 0 at the bottom and around the sides, held at some constant temperature U sub 0 at the top. And U is the steady state temperature in this cylinder. Separated variables using the product method as usual. We got, for positive and negative lambdas anyway, we got equations that were some kind of Bessel equation, and then this familiar second order equation, etc. We looked at the modified Bessel equations and we could reject non-positive lambdas. I'm not going to go through all this again. But applying, solving the partial differential equation and two of those boundary conditions, two of the explicit boundary conditions and the implicit condition of boundedness, we got this solution. We don't have the A sub n's yet because we didn't satisfy the boundary condition of that constant temperature at the top of the sphere. To do that, we expanded that constant temperature with the Fourier-Bessel series, and that was a case 1 type expansion because of the eigenvalue generating relationship. And so we had a formula for the A sub n's. It was this. This was all by review so far. Normally we would stop there, but in this case, we can actually evaluate this integral. So now let's do that. By matching coefficients, we had this. This alpha sub n sinh equals the coefficients of the Fourier-Bessel expansion. Let's see, this just plug in what all the terms are of that expansion, you get this. So this 2 will cancel. We can just have a 2 down here. So that's something we can do right away. We're going to use this Bessel property of the Bessel function. That goes back many recordings ago when we talked about Bessel equations and Bessel functions. So here's what we have. This guy equals that, which was now a 2 at the bottom because that canceled. I can pull out this constant U sub 0, that's up there. What I want inside here, I want it to look like this, like an x, argument of x, dx. So I'll multiply this r and that dr by alpha n. To make up for it, I divide by alpha sub n squared. Then I'm going to set x, substitute variables, set x equal to alpha sub n r. When I do that, when little r equals 0, x will equal 0. When little r equals 2, x will be 2 alpha sub n. You have to change that limit. Now this is an integral, the indefinite integral I can take. It's this. So I'm evaluating that thing between the limits. When x is 0, I'm just going to get 0, so I only need the upper limit. 2 alpha sub n, j sub 1, 2 alpha sub n. Cancel some terms. 2's, one of the alpha n's here, and one of the j's simplifies to this. So now I have a complete solution. Here was my solution from before. Now I have what these big A sub n's are. This divided by the sinh. And now it's all so simple, I can put it all in the sum. Anything that doesn't involve n, I can pull out, and so I could pull out that constant. Anyway, here's the complete solution. I don't have to evaluate any integrals anymore. I just did that. So that's that. And we'll do one more example of cylindrical coordinates, and we're done with that little bit.